Hello, thank you all very much for coming, and welcome to this session on creating high-performance spatial databases with SQL Server 2008. Come in. I'll start by introducing myself. My name's Alistair Aitchison. I'm an independent consultant. I'm based in Norwich, in Norfolk, and I've got a particular interest in spatial databases and spatial applications, typically using SQL Server 2008 as a back-end, and then applications such as Google Earth or Bing Maps as sort of front-end interfaces into that data. I'm also the author of 2 books on SQL Server, Beginning Spatial with SQL Server 2008, which was published at the beginning of this year, and Expert SQL Server 2008 Development, which is actually due out in a few weeks, which I co-authored with a guy called Adam Makinick. Some of the material from this session is going to be based on some of the content from those books, and some of it's brand new. So there should be something new for everyone, whether you've seen that or not before. This is my first time presenting at SQL Bits, so I'm very pleased to be here. Good to see lots of people here as well. We'll see how it goes. So if we have a look at the session plan, this session is going to be looking at the spatial features in SQL Server 2008, particularly from a performance point of view. Okay, so the first thing we're going to look at is a little bit about the different models you can use to store spatial data in SQL Server 2008, and going to ask the question, do you actually need to use the geometry and geography data types? Now, when you're talking about spatial performance, that's intricately linked to the subject of spatial indexes. So we're going to be spending quite a bit of time looking at spatial indexes, both from a sort of a theoretical point of view, and then also going to look at a practical point of view as to how the query processor actually uses spatial indexes to satisfy spatial queries. And then we're going to move on to actually practical tips that you can take away and implement when you get back to improve the speed of your queries. Now, this is a level 400 session, so I'm not going to be doing the introductory sort of explanation of the difference between geometry and geography. I'm hoping that you've got a general awareness of these two types anyway. If you do have any questions, there will be the opportunity for questions at the end of the session, and I'll be hanging around afterwards if you want to come up and ask me anything afterwards. Now, some of the sessions here at SQL Bits have been very demo heavy. They're very kind of, look at the application in action. This session is going to be quite PowerPoint based. I'll set your expectations now. One of the reasons for this is I find when you're thinking about spatial data, it's human nature to think in terms of sort of graphical terms of maps and how things overlap each other. So it's slide based, but there's quite a lot of diagrams, and what I'm actually going to do is step through some spatial queries and try to use diagrams to explain what's going on at each stage of the query process when you run a spatial query. Okay, so we'll start at the beginning, and the first question is, do you actually need to use geometry and geography? Now, it's long been possible to store spatial data in SQL Server. If you were to try and store spatial data in 2000 or 2005, for instance, this is one of the basic models you might have used. So what we've got here is a customers table, and we've got 2 decimal columns at the bottom, which are used to store a latitude and longitude associated with each of our customers. Now, this is not the only model you could have used. It's possible to store binary data. Sort of well-known binary format is a standard format you could have used. But this is a fairly common one that you might have seen and you might be using at the moment. And how can you use that kind of data? Well, using this model, it's possible to answer questions like which of our customers are located in a certain area of space. The query on this slide does that. So select star from customers, where lat between lat-min and lat-max, and long between long-min and long-max. This represents the red rectangle area you see on the map here. The minimum latitude and longitude is located at the bottom left-hand corner, and the top right is the maximum of both values. Now obviously this has got some limitations. The biggest one being it really only works for rectangular areas of space. If you wanted to ask the question of which of our customers lies within a county boundary or a country or a complex polygon, you can't really do that using that approach. What else can you do with the two column model, sorry? Well, you can calculate the distance between 2 points. The formula shown on this slide uses something called the spherical law of cosines. This is not the only way you can approach it. There's another common method called the Haversine method. And what this does is it calculates the distance between 2 points on a sphere, essentially. That constant at the beginning, 3963, that's the radius of the Earth in miles. So if you use this formula, you'll get a distance between 2 points in miles calculated on a perfect sphere. Now, again, this has got problems with it because the world is not a perfect sphere. It's an oblate spheroid is the technical word, which basically means it's a sphere that's been squashed a bit. But it's still, you know, a reasonable approximation for many cases, and it doesn't need geometry and geography. Now, the limitations then of this two-column model. Well, one of the limitations is the fact that because we are only storing a single coordinate value with each row of data, you can really only use it to store point locations in space. You can't store, for instance, routes or areas, polygons, very easily, at least anyway. The calculations on which those coordinates can then be used are normally either based on a flat plane. For instance, if you were storing here in Great Britain, you could be storing national grid coordinates, in which case you do calculations on a flat plane. Or, as in the spherical law of cosines method on the last slide, you can perform calculations on a perfect sphere. But both of these are approximations, so you're going to introduce approximations into your results. And also there's a fairly limited range of methods. We've seen how to work out the distance between 2 points and whether a point is contained within a rectangle. But if you wanted to do more complicated spatial queries, it gets pretty intensive to try to write that in T-SQL. So at this point, along comes SQL Server 2008. And in SQL Server 2008, not only can we store points, we can store line strings, so a connected series of points. We can also store polygons, and we can store complex shapes, so we can have polygons with holes in them, and we can have multi-polygons and geometry collections. And SQL Server 2008 stores spatial data as a CLR UDT type, which means that every individual item of spatial data can be up to 2 gigabytes in size. And that's sufficient to get you know, even the outline of most countries at a reasonable level of detail. So you can get pretty complicated shapes. And when you perform calculations using spatial methods of the geometry and geography data types, those methods perform calculations based on a spatial reference system. Now, for geography, the spatial reference system basically defines the shape of the Earth onto which you're doing your calculations. There's lots of approximations of shapes of the Earth. The one that you're probably most commonly familiar with is something called the WGS84 model, which is what's used by global positioning systems, amongst other things. But there's lots of other models. The NAD83 model in America is a very common geographic model of the Earth. And if you're using the geometry data type, there's also lots of spatial reference systems you can use. You can use state plane coordinate systems, or you can use the national grid here, or in other European countries have national grids as well. So we get much more accurate calculations than we used to be able to do. And thirdly, when Microsoft chose to implement the spatial features in SQL Server 2008, they did so based on the Open Geospatial Consortium Simple Features for SQL specification. Now, the Open Geospatial Consortium, or OGC, this is a cross-industry body which sets standards for spatial features used in Oracle and IBM and SQL Server. Microsoft joined the OGC as a principal partner, and the methods that you use in SQL Server are compatible with the definitions defined by the OGC across these other databases as well. So not only can you do simple intersect queries or work out the distance between points, You can work out whether one polygon is contained within another, for instance, or whether a line crosses over a polygon. Or there's something called the DE9IM, which is the dimensionally extended 9 intersection model. And what that is essentially is it's a mathematical model that allows you to find complex relationships between any two geometries. So at this point, you might think it's a bit of a no-brainer. If you want to implement spatial features in SQL Server 2008, let's use geometry and geography. They're capable of storing more complex data, they're more accurate, and they've got better functionality. As ever, it's not quite that simple. Those enhanced features and that enhanced complexity comes at a cost. And the cost is that spatial queries are probably going to be among the most complex and the slowest queries you're going to run on SQL Server 2008. We're going to look at how you can make them faster in just a second. But the first question really to ask yourselves, and my first performance tip as it were, is to ask whether you really need to use all those spatial features or whether you can make do with the two-column model which you've been able to use for a long time. Not all spatial applications need to use geometry and geography. For example, it's very common to have a web page with a store locator type functionality. So you type your postcode in, and what you get back is the results of your closest 3 stores or whatever features they are, together with the distance away from your location that they are. Now, for that example, each location is only represented as a single point in space. The calculations themselves can be fairly approximate. We're not looking for high accuracy. And in that case, I can almost guarantee you will get better performance using the old model than you will do using geometry and geography. Another example, I don't know if any of you were in the Bing Maps presentation this morning, but it's quite common now to see a web page where users can browse around a map, and the map goes back to SQL Server and returns a list of points of interest located in the currently visible map screen, for instance. Now, because that's a rectangular viewport, the fastest way to retrieve all the information from the database that lies in that viewport is to use that simple rectangular bounding query we saw earlier, where the latitude lies between the minimum and the maximum, and the longitude lies between the minimum and the maximum. That will almost certainly, with the correct index placed on those columns, give you the best performance. So that's the answer to your performance problems. Don't use geometry and geography. Unfortunately, that's probably not going to satisfy most of you, and you're looking for a slightly better answer than that. So let's move on and look at the next step. In order to actually improve the performance of geometry and geography, we need to have a little bit more of a closer look as to how they work, and particularly how spatial indexes work. So let's move on to that now. Before we go any further, it's probably worth explaining a little bit. I've said spatial queries, the term, a couple of times, and it's probably worth explaining a little bit more what I mean when I say spatial queries. If you look at the line at the top of this slide, select star from T where A intersects B equals 1, basically. That's what I mean when I refer to a spatial query, is a query where in the where condition, or in the where clause, sorry, you've got a condition that's using one of the methods of the geometry or geography data type. Now, in this case, I'm using st-intersects. That's probably one of the most common methods you'll find yourself using. And what st-intersects does is it tests whether A and B, as I've got supplied there, have any points in common at all. So it might be that one of them touches another, it might be one of them is contained within another, or that they partially intersect each other, but they've got some points in common. That's st-intersects. Now, when you normally write a spatial query, it's quite common, as in the form I've got here, where A is going to be a column in your table, and B is a parameter supplied to the method that is a fixed search region. So, for instance, if we were looking to find points of interest located in Wales, T might be our table containing countries of the world. A is a geometry or geography column that is containing polygon outlines of each of the shapes. A contains points of interest, I meant to say, and the B parameter supplied is a polygon representing Wales. So you select all the rows from the table that intersect that polygon. That's what I mean by a spatial query. And the key thing to note is that it's based on comparing two geometries or two geography instances. You can't compare a geometry with a geography or a geography with a geometry. They must be of the same type. Okay, and when you execute that query then, what happens? Well, SQL Server uses what's called a two-stage filter to actually process the results of that query. There's a primary filter and there's a secondary filter. The primary filter, as you can see there, it's basically like a first guess at the results. It's an estimate. And what it does is it returns a superset of results that could fulfill that condition in the query. So it's guaranteed to contain all of the results where A does intersect B, but it may also contain a couple of false positive results. And then once you've got the results of the primary filter, that's when the secondary filter then comes in, takes the results of the primary filter and it weeds out those false positive results so that the answer you get at the end is the accurate answer. And these filters work on slightly different sets of data. The primary filter goes to the spatial index of the table if one exists. And the secondary filter then compares the actual values themselves. Okay? If you don't have a spatial index on your table and you run that query against it, all of the work must be done by the secondary filter. And as it says there, the secondary filter is accurate, but it's slow. So when you're creating high-performance queries, what you really want to do is get as much of work as possible done at the primary filter stage. Get that guess to be as good as possible, as fast as possible, and not to contain too many false positives. So how do we do that? Well, we need to now look a little bit about how the index is formed, because the index is where the primary filter looks to get that first guess of results. Now, spatial indexes, I'll say now, work very differently from pretty much any other sort of index in SQL Server. So any preconceptions you might have about indexes at this point might not apply to spatial indexes. Indexes in SQL Server normally use a B-tree structure, and B-trees work very well when your index can be assigned a logical order. So, for example, if you've got decimal data or money data or numeric data of any sort, you can arrange it into numerical order. If you've got string data, chars or varchars, you can put them into a collating sequence like alphabetical order. And if you've got temporal data, you can put that into chronological order. So far, so good. And then we get these spatial types. We've got geometry and geography. How do we put them into an order so we can put them into an index? Well, the answer, or at least the solution used by SQL Server, is to use a grid system. And it uses, in fact, a multi-level grid system. It's got 4 levels of grid. And in this slide, we're going to step through how that index is constructed, okay? So, suppose we have a table that's got a geometry column, and that column contains data representing countries of the whole world, which is what we've got shown here. When you create an index on that column, what you do is you overlay a grid over the whole extent of data in the table to be indexed. And that's your level 1 grid. So here we've got a level 1 grid that's a 4x4 grid of cells. Okay? Now you can actually configure how many cells there are at each level of the grid. 4x4 is the low resolution. You can also do a medium resolution grid, which is 8x8. And you can do a high resolution, which is 16x16. But for this example, I'm just going to use 4x4, partly because it's easier to see on the screen. So we've got a level 1 grid, and that covers the whole area of space that's going to be included in the index. And then within each of those level 1 cells, we then have an entire level 2 index. So if we choose that cell, for instance, and zoom in on it, what we're now looking at is that level 1 cell, which has been decomposed into an entire level 2 grid. And this level 2 grid is also 4x4, although it could be 8x8 or 16x16. You can alter the grid resolutions at each of the 4 levels independently. And then within each of those level 2 grid cells, we have an entire level 3 grid, and you can probably guess what's coming. Within each of those level 3 cells, we have a level 4 grid. So we have 4 levels of nested grids, essentially, that decompose our entire data that's going to be indexed. Now, if you use the low resolution at each of the 4 levels, as I've done here, you've got 4 by 4, so you've got 16 cells at each level, so you end up with 65,000 level 4 cells potentially going to be in your index. If you choose high, you've got 256 cells at each level, so you then end up with 4.3 billion level 4 cells. So you can get very, very high resolution indexes with high, but that's not always a good thing, which we'll come on to later. So we've got a grid, but we haven't yet got an index. How do we go from that grid to an index which we can actually use to satisfy queries? Well, what the index does is having overlaid those grids, what we want to look at is those cells in the grid that either are totally covered by the geometry, or they're partially covered, so some part of the geometry touches that cell, or they simply touch it at a point adjacent to the geometry. And we can look at cells from any one of those 4 grid levels and include them in the index, but we don't want to include every cell at every grid level. If we did that, our index would be very large, for one thing, and also we'd be failing to take advantage of some of the kind of neat features of this nested grid system. Okay? What we want our index to do is we want it to contain this approximation of our geometry, and we want that approximation to be as good as possible so that our primary filter is efficient. But we also don't want our index to be too large, because then it will take too long to query and it will kind of defeat the point of having the index in the first place. So there's 3 rules which SQL Server applies, and these rules are all intended to basically get the grid cells which will help describe the approximate shape of each of these objects with the maximum amount of accuracy, but requiring the least number of cells to do so. And they're called the covering rule, the deepest cell rule, and the cells per object rule. And if we just have a look at each one in turn. Right, the covering rule to start with. If a grid cell is completely covered by geometry, don't further subdivide that cell. What does that mean? Well, what the diagram here is showing, this is a geometry, and I've overlaid it with all 4 levels of the grid, so you can see them all at once. Okay, you've got level 1, which are the big cells. Each of those is divided into level 2, 3, and 4, which are the tiny little ones. Okay, and what the covering rule says is if you look at these 2 large level 1 cells in the middle of the geometry, looking at level 1 alone, we know that the whole of those cells has been intersected by the green polygon, okay? Therefore, by implication, every one of the level 2 cells contained within those level 1 cells must also be totally covered, and the level 3 cells beyond that, and the level 4 cells. So it wouldn't add any more information to our index if we bothered storing those grid cells as well. All we do is we store the level 1 cell. We say this is totally covered, and that's all the information we need to know. We then go on to the next rule, which is the deepest cell rule. Now, the deepest cell rule is a little bit like the covering rule in reverse. And what this says is, if a cell has been subdivided, so we've gone down to one of the deeper levels, only store the intersecting cells at the deepest grid level. So for this example, if you have a look at one of the little cells around the edges of the geometry where we have drilled through right to level 4, each level 4 cell can only be contained in one level 3 cell, which in turn is only contained in one level 2 cell. So if we know that one of those tiny little grid cells there at level 4 partially intersects the geometry, we know, again by implication, that the level 3 cell in which it lies must partially intersect the geometry, because the part of it that contains that level 4 cell intersects it. So when we have drilled down to a deep level, don't bother storing the level 1 and the level 2 cells. That's the second rule. And the third rule is a cells per object rule. If subdividing a cell would exceed the maximum allowed number of cells for each object, do not subdivide the cell. Now, this rule is a little bit like it's kind of like a hard limit that you can set to prevent your index entries growing too large. Even after having applied the covering rule and the cells per object rule, and the deepest cell rule, you can still require a lot of individual cells to fully describe the extent of a geometry, and that would make your index too unwieldy in certain circumstances to be useful. So the cells per object rule basically says once you hit a certain limit, don't bother looking any deeper to try to get more resolution of this index. Let's just call a halt there and we'll settle for the approximation we're currently at. The default value for cells per object is 16, and that's been chosen to work quite well in most circumstances, but we'll go on to a practical example about how you might want to change that a bit later. If you set cells per object too low, then what will happen is that you're not allowing your index to contain those more granular levels of level 3 and level 4 cells, which means that your primary filter of the index is going to contain more false positives. Okay, that's the theory, and now we're going to look at how that theory of the grid and the index is actually used in practice now by SQL Server to run a couple of SQL queries. There we go. Okay, so to do this, first of all, here's the T-SQL required just to create a simple table. And this table contains two columns. It's got an ID column, which is just a char column, and we've got a shape column, which is a geometry column. Now, the only other point to note here is I've added a clustered primary key to the table. Now, once we've followed the rules we just heard about, the grid cells, things like that, we've got down to our list of grid cells, which we're going to use to describe this geometry. The structure of the spatial index itself then is essentially a lookup from each grid cell reference to the primary key of the shape that occupies that grid. Okay? So before you can create a spatial index on a table, it must contain a clustered primary key, because that's going to be the key which we actually look into to say which one of the rows intersected this grid cell. Yes? No, it doesn't have to be an integer. It just has to be there must be a primary key on the table, but no, it doesn't have to be an integer. Okay, so we've got our table, and now I'm just going to chuck some points into it. I've got 4 points here, and to add these points, I'm using the point method of the geometry data type, which takes 3 arguments. It's got the x coordinates, the y coordinates, and then the spatial reference ID. Now, for this example, I'm just talking about some abstract points. I'm not particularly talking about a model of the Earth or anything, so I'm just using 0 as the spatial reference ID in every case. Okay? And so we've got a table, we've got some points in it. Now we can get on to the matter of actually creating the spatial index. Now, this is a bit of a complicated query, so I just want to step it through line by line. The very top line, well, that's just the normal T-SQL syntax for creating any sort of query, except for the word spatial. So create spatial index, then the name of the index, and the table and the column on which you want to create the index. The only point to note about that is it's possible to create multiple spatial indexes on the same column, and each of those indexes can have different grid resolution settings. So you might want to contain the same information in a high resolution grid and a low resolution grid, and then direct different sorts of queries to use the different indexes. Now, shape was a geometry column, so we're going to use the geometry grid for this example. If it had been a geography column, we'd use the geography grid instead. And then we look at the parameters of the index, is what comes up now. Now, the bounding box is the complete area of space that we're going to decompose into our grid. In this case, I'm starting at a point at 0, 0, and I'm going up to a point at 4096, 4096, so this is a square, essentially. Those values have been chosen for a reason, which you'll see in a second. It's worth mentioning, if you're using the geography data type, you don't need to specify a bounding box. In fact, you can't specify a bounding box. Because the geography data type works on a globe, the bounding box is implicitly assumed to cover the complete globe. You can't index only a portion of that globe. But with the geometry data type, which operates on a flat plane, which potentially extends to infinity in every dimension, you must specify the bounding box. And then we're doing the grids. So again, I'm using medium resolution at every one of the 4 levels for this. So that's an 8 by 8 grid. And I'm keeping the cells per object limit at 16, which is the default. Now, I said there was a reason why I'd chosen those values there. And the reason is because if I use a medium grid resolution at each of the 4 levels of the grid, and my level 1 grid extends from 00 to 4096, 4096, each of my level 1 cells decomposes that space into an 8 by 8 grid. So each level 1 cell ends up being 512 by 512. Each level 2 cell divides that into 8 again. So what we've ended up with is each level 4 cell for this example is a 1 unit high by 1 unit wide cell. And that's just going to make the diagrams a bit easier to follow in the next section, basically. Okay, so if we just have a little bit of a look at a picture, this is what our table now looks like. So we've got our 4 points, A, B, C, and D. And the dotted lines there represent the level 4 grid cells in our index. Now let's suppose we actually wanted to write a bit of a query, and we wanted to find out which of those 4 cells lay within this red polygon. Now, obviously, these are very basic examples, but this same sort of query is exactly the thing you'd write to find out, how many crimes were there in this county, or which of these customers lies within this sales territory. These are all the same sorts of queries, and SQL Server uses the same sort of processing. But to try to really step it through simply, we're going to keep it as basic as we can. And here's the query that you might write to answer that question, which of those points lay within the polygon. So you define a new variable, which is a geometry variable, and that polygon definition there in red at the top, that's simply the red square which you saw on the last slide. And then we select all those rows from the table where the shape column intersects that polygon. Now when you run that query and you look at the execution plan, you'll see something that looks a little bit like this. It looks quite complicated for a query that apparently was quite simple, but I don't want you to worry too much about it. The thing that you need to pay attention to is over on the right-hand side down there. And if we highlight that item, you'll see it says clustered index seek spatial. So looking at the query plan, we know that the query processor is choosing a plan that's hitting the spatial index. But we don't really know yet what it's doing when it gets that index. How does it do the primary filter? How does it do the secondary filter? And how is that influencing the performance of the query? Fortunately, SQL Server comes with a new stored procedure, or actually a set of system stored procedures that are specifically designed for analysing and explaining the performance of spatial queries. And we're going to use one called SP-Help Spatial Geometry Index. Again, there's a sister stored procedure to this called SP-Help Spatial Geography Index, and each one of them also has XML versions which dump the output as XML rather than a table data set. And the parameters I've supplied here to the index, I've supplied the table name, the index name that I want to find out more information about. I'm also going to choose the verbose output setting to get a bit more information. And then the important thing is you supply what's called a query sample to this query. Remember that when we defined what I meant by a spatial query, we're talking about a comparison between 2 geometries or 2 geographies. When we run this spatial index, we're supplying the column in the table as one of the things to which we're making a comparison. But then we also need to tell the stored procedure, okay, well, what's the other thing we're going to compare this column of data to? And that's called the query sample. So for this example, again, I'm using in red there, that's the definition of that red square. So we've got a table containing points, that's what's been indexed, and I want to find out, using this stored procedure, how is SQL Server going to find out which of those points lies within this query sample? And you get lots of data from this stored procedure. You get a couple of hundred lines of interesting information. And we're just going to step through some of the important ones. So the first one, number of object cells in level 4 in index 4. Well, that's not particularly surprising. Our table contains 4 points. Each one of them lies in its own level 4 cell. So we've got 4 level 4 cells in the index. There they are. The next thing, and this is an important point, I'm going to stress this a bit. When you're comparing those two geometries, the query sample and the points in the index, both of them must be tessellated down to the same index grid. So though the index only exists on the table, in order to do the primary filter against that query sample, we're going to compare the query sample to the same index, okay? To the same grid, sorry. So we also say, how many level 4 cells are there in the query sample? Well, there are 8 cells around the outside that partially intersect the geometry, and there's also 1 cell in the middle there that's completely covered. And we store all of those in the index, and we also store a little flag to say, was this partially intersected or fully covered? And we'll use that flag in a minute to answer one of the questions. And then the primary filter, when we say which of these points lies within the polygon, what the primary filter does essentially is it doesn't look at the points in the polygon at all. What it does is it looks at the grid cells that are occupied by the points and the grid cells that are occupied by the polygon, and it compares them. And on the basis of that comparison, this is how our primary filter can make its guess as to which of the points actually satisfy the query. For example, point A lies or partially intersects a cell that doesn't have any cells in common with the polygon, okay? That blue cell there doesn't have anything with the polygon at all. So we know, based on the primary filter alone, that that point definitely can't lie within the polygon, and we can exclude it from the primary filter. So that's 25% of the rows from our base table. We don't have to bother calling ST intersects on them because we know that they can be excluded. That leaves us with the remaining 3 points, and they are selected by the primary filter. Now, at this point, you might think, okay, so we've got the other 3 rows. All of those have to be passed from the primary filter to the secondary filter. But actually, we can do a little bit better than that. Point B, Point B partially intersects a cell that was totally covered by the red polygon. Now, in that circumstance, we know that point B itself must lie within the red polygon. There's no way it could partially lie in a square that was totally covered and not be included itself. So point B, we can pre-select based on the primary filter alone. Again, we don't have to call the secondary filter. So 33% of the rows selected by the primary filter can be included in the result set, and that's called the internal filter when we're able to do that. And that leaves us with the remaining 2 points, C and D, that we're not sure, basically, based on the primary filter alone, if they're inside or outside the polygon. Let's call the secondary filter. The secondary filter is essentially the ST intersects method itself, and that's going to compare the individual point sets of the geometry to come out with the right result. So there's 2 rows output. The 2 rows are B and C. We knew that at the start. It was obvious to us they're contained in the polygon, but that's how SQL Server processes it. And the important thing to know is whatever grid settings we'd use there, if we'd had high resolution, low resolution, no grid at all, we'd always get the same results. We'd always have B and C be the answer. But the difference is how those results were obtained. Could they be discarded from the primary filter? Could they be pre-selected by the primary filter? Or would they have to go through the secondary filter? And that's what makes the difference to the speed of your queries, really. What you want is to get that primary filter as efficient as possible. When we come to measure how good the primary filter being, there's 2 efficiency measures we use. The first is one called the primary filter efficiency. And what that is it's a measure of the number of rows selected by the primary filter, how many of them ended up being correct, essentially. So the primary filter selected B, C and D, and of those B and C were correct. So our primary filter efficiency in this case was 66%. The internal filter efficiency is another measure, and this one says of the rows that were in the final output, how many of them were selected from the internal filter. And in that case, it's B out of B and C. So we've got 50% for our internal filter efficiency. And what you really want to try and do is maximise both of those two efficiency ratings, your internal filter efficiency rating and your primary filter efficiency rating. And I'd just like to say, I can't remember if I said at the beginning, but all of the T-SQL code I used to create those examples is all available for download, so you can go and try experimenting yourself with different settings for the grid resolutions and see if you can get those figures maximised. Okay, so we've looked at the theory and the practice of spatial indexes. Now we'll get on to the stuff about what can you actually do to get your queries to perform faster. How do you get that primary filter to be efficient? Well, the first thing you need to do is you actually need to use a supported method. Normally in SQL Server, when you create an index on a table, you don't need to worry too much about how SQL Server uses it. You create the index, and when the query optimizer chooses what plan to use to run the query, if that index results in the least cost query, it'll choose the index. You don't really think about it too much. It's not quite the same with spatial. Firstly, only certain spatial methods can make use of the index. st-intersects, which is what I've been using for all these examples, can, and so can the specific subtypes of intersection query as well, so contains within touches. You can also use st-distance so long as you are identifying geometries that lie within a certain distance of another. You can't use distances beyond a certain distance, okay? So that's distance closer than this. And you can also use filter. Filter is an interesting method because filter essentially only uses the primary filter. It doesn't go through that secondary filter stage of getting rid of the false positives. So filter will give you an approximate answer, or it may give you an approximate answer, based on a primary filter alone. Even when you've used one of these methods, you've then got to use the right syntax. SQL Server is a little bit picky about the syntax you use. And even though they're logically equivalent, you must write A intersects B equals 1, or true, rather than 1 equals A intersects B. That won't allow the index to be used. So that's just something you just need to get right, basically. Now, in the original RTM release of SQL Server 2008, there was a bit of a bug in the cost estimations that were applied to spatial queries. As you probably know, when you execute a query in SQL Server, what happens is a number of different plans are created, and a cost estimate is put with each of those plans, and the plan with the least cost is the one that gets chosen to execute the query. Now, what was happening is essentially spatial indexes weren't being costed correctly, and so sometimes the correct plan wasn't being chosen by the query optimizer. Now, Service Pack 1 does improve that situation slightly. So if you haven't already upgraded to SP1, I do recommend that as a way of getting more reliable cost estimates. Even after having applied SP1 though, you may find that you still need to add a manual index hint to your queries. So rather than saying select star from table, you might need to do select star from table with, and then the name of the index to force the query optimizer to use a spatial index. Otherwise it just doesn't get picked up sometimes. Once you've made sure your index is being used, you need to make sure the index is effective. Remember, there's three possible outcomes. There was that internal filter. We know this row can be included in the results. Or there's discarding it. We know this row definitely isn't in the results. And both of those two, from your point of view, are good things. Those are the two outcomes that you want to be getting as a result of your primary filter. The secondary filter, where, well, we're not really sure we have to run the secondary filter, that's what's going to slow your queries down, okay? And what you need to do is you need to choose those index parameters, the bounding box, the grid resolutions at each of the 4 levels, and the cells per object, to match both the data in your table itself and also the sorts of queries that you execute against that table. Remember that what we're doing is we're making a comparison between two sorts of geometries, and those geometries must be tessellated according to the same index. One of the sort of common problems I see occurring most often is people who choose index settings based on the contents of the table alone. For example, if you've got a table that only contains points, you've got points of interest, and you might think for that example, the best index is going to be high at every resolution of the grid, high, 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 high. That's going to give you the smallest possible boxes, it's going to give you the least false positive results. The problem with that is, though, if you then are trying to find out which of those points lies within a complex, large shape, say Australia or something like that, you're going to be trying to get that polygon of Australia to match the same index settings as you had for your points in order to be able to do the comparison. That's not going to be a very good query. So have consideration for both. As a little demo of that, this was the results we had of our query earlier that had medium at all 4 levels of the grid. There's our 4 points, and there was our polygon. Let's see what would happen if we changed that level 4 to be a high grid resolution instead. Essentially what would happen is every level 4 cell would become half as wide, half as high. So this is our new grid. And then when we do the tessellation on this grid, what happens? Well, points C and D over the right-hand side, they now partially intersect a cell, and it's a smaller cell. So you think, well, that's good. That's got to be a more accurate estimation when you use those. But points A and B, what they do is they now lie on the border of 4 cells, in fact. They're lying there. And each one of those cells, because being on the border counts as touching a cell and therefore intersecting it, every one of those 4 cells must be stored in the index. So the examples in that case hasn't become really any more accurate. And what's even worse is when we then come to tessellate the red polygon to that same index, we find out that we now need 36 cells to fully cover that shape, to fully describe that shape. There's 32 partially or border cells around the edge, and there's 4 fully contained cells in the centre. And what that will probably do is that will blow your cells per object limit. As a result, we'll start counting, and when we get to 16 cells that have been tessellated, or whatever your object limit is, we're going to stop the tessellation and we'll say, okay, we'll give up, that's a good enough approximation. And you'll only get the level 3 cell instead of fully going down to the level 4. So bear in mind not just what's in your table, but also the sort of queries that are running against it. Practical tip, how do you improve performance then? So you make the bounding box as tight as possible. If you shrink the bounding box to fit very tightly over your table of data, each individual grid cell within that bounding box is going to be smaller, and that will be more accurate. Having said that, you don't want to make your bounding box so small that you've got data that lies outside the bounding box, because if you have that, it's not going to be included in your index at all, and therefore you can't get the primary filter of that data. As you've just seen on the last slide, if you increase the grid resolution of your indexes, you might need to increase the cells per object limit to go hand in hand with that to make sure that you are allowing your index to fully tessellate your objects. You can have multiple indexes, and those can be at different resolutions. The example I like for this is, suppose you've got a table of data that contains details of customers in Britain and in the US. And if you were to try to create a single index to index all of that data, what you'd end up doing is you'd draw a level 1 grid from the west coast of America over to the east coast of Britain. And a large part of what you'd be indexing would basically be the Atlantic Ocean, where you don't have any customers lying. You'd probably get a lot better resolution if you had 2 indexes, one over mainland America and one over Britain, and then you just directed your query to use the appropriate index to satisfy the query. Use non-spatial predicates. By that, what I mean is that remember that you can use conditions, spatial conditions in the where clause of your query alongside, normal T-SQL. So if you were to try to identify towns in Wales that had a population of greater than 10,000 people, for instance, the spatial component of that is probably going to be the more complex condition. So don't first identify all towns in Wales and then of those work out how many have got over 10,000 inhabitants. Cut down your data set first to identify just those towns that have got 10,000 inhabitants, then find out which of them in Wales, and you'll probably get better performance. Reduce unnecessary detail. Now, particularly when you download data off the internet or from other sources, you may find you don't get that much control over the level of detail that it comes in at. Although it doesn't make a difference to the primary filter, when you get to the secondary filter, where you're actually comparing the point sets in both geometries, complicated shapes that have lots of unnecessary points are going to be a lot slower than simpler shapes. So if you've got an application that has, global sales territories or something like that, where you really don't need, millimeter resolution of your objects, you can use the reduce method in SQL Server 2008, and what that will do is generalize shapes. So you've still got the overall shape of each of the points in your table, or the polygons in your table, but it's cut out a lot of the intermediate points that don't really add much to the shape, and that will make it a lot quicker. And my final comment there is experiment. Spatial is still a new feature. Certainly in the SQL Server 2008 world, it's very new. It's existed for a little bit longer in Oracle and DB2 and things like that, but people are still learning, really, what the best way to do certain things is. There isn't much in the way of best practice yet, and it does depend a lot on the particular structure of your data and how you're using it. So don't be afraid to sort of try different settings and see really what works for you. If you want to know any more, well, like I said, there's Beginning Spatial. I've got a couple of copies here at the end. If anyone asks a really good question, I might give them out. Or there's also the MSDN Spatial Forum. If you're not familiar with the MSDN forums, they're really good places to go, actually. A lot of the guys who are on the SQL Spatial team in America do check in very regularly at the forums. They're very helpful, and it's a good place to ask questions. And there's lots of MVPs and myself and other people hang out there as well, so it's a good place to ask questions. My email at the bottom. If any of you have any questions, please do feel free to contact me. I'll do my best to see if I can answer any questions. Like I say, I do encourage you really to go out and try it yourself, because although you can see slides and pictures and things, it's not quite the same as trying it out yourself and seeing the results dynamically as you alter the boxes. So all the code, all the slides, everything is going to be on the SQLBit website.